So this is a play, or at least a poorly made paper model by a 17-year-old who just happens to be me. Let's see if it flies. Well, it did, but the one made over 120 years ago by the Wright brothers near Kitty Hawk on December 17th, 1903 did fly. Oliver and Wilbur Wright changed the world by creating the first heavier-than-air aircraft. This invention opened our doors to a new form of exploration. But we humans are a curious and a glorious bunch. We didn't just stop at the skies, but we looked forward and forth to the heavens. In just around 40 years, Goddard had made the first rocket. Germany had made the first orbital satellite, and Russia had launched the first suborbital satellite. In 1969, the Apollo moonshot took us to the places which we thought we'd never see. But today, space exploration is a topic of vital importance to both national security and global scientific studies. Since there are many space organizations all across the world, it is a heavily discussed matter all across the globe. But today, still, launching rockets is not the most easiest and the least expensive thing you can do. And this technology is out of the reach of an average scientist. Well, there are many problems with the current launch systems, like they are highly inefficient and they are highly inefficient and they require tons of fuel. For example, the LBM Mark III, or previously named GSLV Mark III, requires 340 tons of fuel to just reach geosynchronous orbits. Geosynchronous orbit. That is a fuel to payload ratio of 85:1, and that sounds ridiculous, but it is true. As to improve this technology, we pondered upon various solutions, but still there was many other problems. Like the systems like these are very costly. To launch a single kilogram of matter to space, we must spend $4,000 to just get it there. Now, our behavior as a species has not been very great, and we generally try to destroy ourselves with various wars and stuff. But if we manage to survive till the end, we may need to get off this rock to another one. For this, we need to scope out the universe. And for that, the frequency of launches must be increased. Well, the problem then there is a problem again. Many commercial space research agencies have come up with reusable rockets, but they are not as efficient and economical. Then there's the sustainability. Every kilogram of space requires the evolution of many tons of carbon dioxide in the atmosphere, along with many other toxic gases. It is almost a matter of shame for us as a species that we haven't been able to make space accessible for everyone in the 21st century. And only billionaires can send their cars to space just for fun. Well, we may have the solution. The electromagnetic railgun launch deployer, a project which me and my friends worked for about 3 to 4 months, analyzed various researchers by many other great scientists, and we came to a conclusion that technologies which are used for weapons today can be used for betterment of humanity. Well, as the name suggests, the electromagnetic railgun launch deployer uses a railgun powered by electromagnets to launch payloads into the atmosphere. So you may be wondering, what is a railgun? Well, imagine a rectangle imagine a rectangular coil made up of any conductor. Now imagine that one of its sides is movable. If you attach a battery in one of its ends, you will get a current through the loop. Now, if there is a magnetic field perpendicular to the loop, there is an interaction between the magnetic field and the current through the movable side. This interaction generates a force which propels the movable side forward or backward depending on the direction of the magnetic field and the current. Therefore, essentially, a railgun is a linear DC motor with various with a pair of parallel rails conducting electricity which carry current to and from a connecting link which acts as a payload. The rails acts as single field turn winding, as can be shown from the video. So this magnetic field propels the payload forward. The Lorentz force acting due to the interaction of the current and the magnetic field propels the payload ahead with a great velocity. Now, the system is still being used in various systems like a roller coaster, and is being heavily researched by the US Navy for making weapons. That is where we came about those research papers. They may have been classified, but we don't know. There are three primary concepts at play here. That is okay. So that is the electromagnetic propulsion, the conservation of momentum, and the ionic propulsion systems. Now the principle is that two conducting rails are connected to the power source with a movable payload mounted atop a movable armature. As the armature moves forwards, the magnetic field propels the armature with an even greater velocity. Then there's the conservation of momentum. Well, as the armature as the armature reaches to the end, it does not get blasted off, but instead is blocked by an obstacle. This obstacle provides a sudden stop, and the payload atop it is free to move and is accelerated off with an even greater velocity thanks to the conservation of momentum. Also, there is ionic propulsion. There are ionic propulsion systems mounted atop the payload, which may provide an additional boost during launch and can also serve to provide course corrections when the payload is in space. Now, let me just go through some slides here. So now, as to calculate the magnetic field acting on the payload, we can use the Bowers-Schwarz law to get a following function of the magnetic field with respect to the position of the armature. This can be further allowed to calculate the force acting on the armature using the Lorentz force, which will be seen in a short time due to a delay. So this payload, this force can be described through an integral, which is the product of the current and the magnetic field under the limits of the width of the payload. Now integrating the first equation into the second one, we get a horrifying math equation, which will be coming up soon. There's a short delay, which may look horrifying to some of you, but that actually allows the payload to be accelerated off with a quick velocity, thus reducing the launch times to only 74 seconds instead of the usual 400 to 500 seconds. Well, the important question is, would you be able to ride it? Well, I had a funny slide prepared for that, but unfortunately it is not visible. So the problem with humans is that we cannot withstand high amounts of acceleration for a long duration time. Like normal humans can only withstand about 20 Gs of acceleration for around 5 to 10 seconds, and more professional trained humans like astronauts and jet pilots can withstand up to 38 Gs of the acceleration for the same amount of time. But since our launch time is about 74 seconds and the presentation is moving again, so let's wait for that for 5 seconds. Yeah, okay. We are down the cost and the slide is visible. So as to, I told you about this equation. This may look horrifying a bit, but that's the course. So as to make this system effective for us today, we decided to just remove the humans from equations and use machines instead, because they have no problem withstanding around 50 to 100 Gs of acceleration. Well, this reduces our track length to about 45 kilometers, with each track requiring around $25 million to construct. Thus propelling our cost for just creating the track to $1.125 billion. $5 million additional dollars to construct the solar array to power the railgun, and $100 million extra for other miscellaneous costs like the construction of the payload, etc. Well, this may sound a lot as the total comes out to be $1.23 billion, but it is actually very, very economical, since it is almost equal to 30 Falcon 9 launches, whereas in this very year, 40 million launches took place. This reduces the effective price of a single kilogram to go in space to only about $100. So maybe you would also be able to send your car to space if you want to do so. What is stopping us? Well, nothing except the government, but nothing except the government, and we can use this system on various other heavenly bodies as well, like the Moon and the Mars. We can make checkpoints there as many chemicals like methane, hydrogen, oxygen, etc., though available on Earth, are not available there, so we can't burn them as emitters. So using this system, it would be even more beneficial since the effect of planetary gravitation in these systems is much less as compared to Earth. Well, this can propel us to infinity, and well, I should stop there before Pixar sues me. And you may be wondering how far this idea may bring forth. So what about those funky space wizards with their cool laser swords? Well, that is a bit far-fetched. But on a serious note, the cons of the system are are very insignificant as compared to the pros, as the system is more efficient than the current technology and can be used to propel us forward into the future. The idea is to use the system for the betterment of humanity, not for destruction. As the quote suggests, for Aspera ad Astra, that is, through hardships to the stars. Thank you.